All right, so let's get started. Okay, I just want to remind you guys homework is due now tomorrow. Okay, so number 2 is due tomorrow. And then for exam number 1 arrangement, so it's going to take place on Monday, February the 8th. So you guys, Wednesday lab attendees will be in faculty 108, and Friday lab attendees will be in this room over here. Okay. All right. For classroom disinfection, today it's assigned to Caitlin and Cassandra. All right. So last time we start chapter 15 on the heat and law of thermodynamics. Okay, and then we talk about the first law of thermodynamics. So basically, it says the internal energy change of the system is equal to the heat added to the system minus the work done by the system on the outside environment. Okay, now this first law of thermodynamics, actually it's not new thing that we learned. We learned this in last semester when we talked about energy. So there's a part we talked about conservation of energy. So first law of thermodynamics is actually basically a version of the conservation of energy that is used in thermodynamics here. Okay, so basically, law of conservation of energy says that total energy of the system should should be conserved. Okay, so that means it's a constant. You cannot create new energy, or energy cannot be destroyed. Okay, it simply just goes from one form to another. So for this example, internal energy change comes as two forms. If there's heat added, so heat is a form of energy. Also, work is a form of energy. Okay, so comes from those two forms of change. So basically, conservation of energy, and then we have been using this law for at least a couple years for now. So it's been proven that is true. Okay, so I just want to reflect this on our faith here. So a lot of scientists try to explain our world just from a scientific point of view. So this theory, I think you guys are pretty familiar with it. It's called the Big Bang theory. So basically it describes how the universe was born and then what happened afterward. Okay, so but according to conservation of energy, so you cannot have energy that is created on an isolated system. So our universe is a isolated system. You can treat it that way. But then what happens when the universe was born? So this theory, although science try to explain it purely from a scientific point of view, but it clearly shows us that at the very beginning, the universe was created. Okay, so that's consistent with our phase of creation of the universe. Okay, so but the Big Bang theory has its success like in explaining what happens after it was created or it was born. So to just put in that point of view. Okay, so but there's this tiny flaw of it, like how it was born or how it was created. So this theory directly actually point to the creation theory of our universe. Okay, in that sense. All right. Now let's get back to the textbook here. So after the first law of thermodynamics was explicitly expressed, we have been taking advantage of it. Okay, so the machines were designed to help us doing actually led to the industrial revolution. But basically, you can have heat. All right, so the most famous one is the heat engine. Okay, that was invented. So you can take heat from a source called the reservoir, and then the heat takes in through a system. It's called the heat engine. So it could convert part of the heat it takes in, and then convert it to mechanical energy, and then the rest will be heat will be dumped into the outside environment. Okay, So this is again delta U equals to Q minus W. In this case, because for engine to work, it always returns to its initial status. So it's a cyclic process. So delta U should be equal to 0. Okay, so then W is equal to the net Q in minus Q out. Okay. All right. And we took a look at some simple thermal processes, like for isobaric or constant pressure process. You can calculate the work done by the system. That should be equal to P times change in volume. All right. For isochronic, chloric, which means volume is constant. So then work equal to 0 because there's no change in volume, or the system doesn't expand or shrink. So it's not interacting with the outside surrounding mechanically wise. Okay. So W is equal to 0. For isothermal process, the temperature is constant. So in that sense, for an ideal gas, the internal energy change is only determined by if there's a change in temperature. So if there's no change in temperature, delta U will be equal to 0. Delta U equal to Q minus W, then Q equals to W, okay, in that sense. For adiabatic process, there's no heat transfer, okay, so Q is equal to 0, okay. We are going to take a look on now the second law of thermodynamics here today. So there's quite a few statements, different statements describing second law of thermodynamics, but fundamentally they are the same thing. Okay, so the first one would be you can put in this way. So if you have a hot object, if you have a cold object, if you have then put in contact, so then the heat will transfer, or heat transfer will occur automatically or spontaneously from the hot object to a cold object. Okay, so that's the first law of thermodynamics. So basically it says heat transfer from hot object to cold object spontaneously. Okay. All right. So in that case, you can put the engine in between the two objects, okay, hot object and cold object, and then you can convert the part of the heat it takes in, and then convert into mechanical work, and then the rest heat can be dumped into the low temperature object there, okay. So then W equals to Q minus QH minus QC in that sense, and these days, I think you guys are familiar with the engine in the car. So this is a full picture of what how it looks when it's working. I think we also mentioned about this last time, but just a slightly simpler version. But here, the chamber here, it takes in fuel and air mixture, okay, and then closes, and then at the next moment, the spark here will ignite the mixture of the gas and air, and then we'll make this in combustion. So then a lot of chemical energy will be released due to combustion there. So it will create a lot of pressure that pushes the piston. Okay, so that's the mechanical work being done. All right, after that is done, then this will go back. Okay, the exhausted heat will carry our exhausted gas here will carry the excess heat that is remaining, or Q of C that is being dumped to the environment. So that's a full cycle. Okay, so then push this piston up over here again. All right. So basically, if you put into a PV diagram, okay, so then this is what it looks like. Okay, assuming if the process happens slowly, okay, so in reality it happens so fast, but we are going to assume it happens so slowly, so we can treat them as quasi-static processes. Okay, and then based on that, we could possibly have a limit of how much work you can convert from the heat takes in. So basically, if you start from point A to B, C, D, and back to A, so then this is a full cycle of the engine, okay, a cyclic process of it. And Last time we talked about in a PV diagram, you can calculate the work done by the process by calculating the area enclosed by the full process, right? So in this sense over here, or it could be a rectangular loop, or it could be any shapes of loop. So in this case, then you can calculate what's the area that is enclosed by this cyclic process. So calculate this area, and then that will be equal to the work done by the engine. Okay, and heat takes in, you can also calculate it, and then heat takes out. Okay, so you can have a sense of how much work can be done during this a cycle like this. Okay, so this one and this one in reality they happen very quickly, so you can treat them as adiabatic process. Okay, so there's heat is not being transferred, but heat transfer occurs in this process and then this process over here. Okay, so takes in, heat takes in, and then heat dumped out, and then during the process you'll do work. Okay, so the work done is equal to heat takes in minus heat dumped out to the surrounding. All right, so basically, this is a simplified schematic drawing of what happens for engine. Okay, so it takes in heat, convert part of heat into mechanical work, and then dump out the rest of heat to the surrounding. Okay, now there's another statement on second law of thermodynamics. So basically, it says it's impossible in any system for heat transfer from a reservoir to complete converted to work in a cyclic process. So that means if you want to convert this heat takes in 100% to the work, that's not possible. Okay, there's some cost during the process, which means this cannot be zero. Okay, so you couldn't convert all the heat into work. Okay, so this is the second statement of this second law of thermodynamics. Okay, all right. So for a heat engine, there are three parts here, three components: a hot reservoir, and there's an engine that does work. There's a cold reservoir or lower temperature reservoir, okay, where you dump the heat into. Okay, so for your car engine, the hot reservoir will be the air in the chamber that is already um, for that is the fuel combustion of the fuel created the hot temperature in the air. Okay, so that the heated air is your hot reservoir, and then the engine does the work to your wheels, and then the cold reservoir in that sense would be the outside air. Okay, all the environment, all the surrounding air. Okay, all right. So for a heat engine, one thing we are particularly interested in is how efficient is the heat engine. So that means the amount of work done, all right, divided by the amount of heat it takes in. Okay, so it uses this amount of heat, then convert to how much work. So that's the efficiency of the engine. So E for the efficiency equal to work done divided by Q it takes in. Now work done can be also written as Q takes in minus Q it dumped out, or QH minus QC. Okay, so all these three expressions, they are the same. Okay, so basically it just depends on what quantities are given, then you're going to pick from one of these three expressions to calculate the efficiency of the engine. Okay, or this one and this one are identical because it's just rearrangement of the terms, or QC over QC, or QH divided by QH gives you 1 here, and then minus QC over QH. Okay, so I should say just maybe just two expression, this guy and this guy, or this guy. Okay, so the last two are the same. All right. So one thing to keep in mind, so for engine to run, there must be a temperature difference, okay, between the two reservoirs. Okay, you cannot have the two reservoirs to have the same temperature. In that sense, then there will be no heat flow through the system, right? So if no heat flow, then you cannot convert heat into work. Okay. All right. So let's take a look on the first example or exercise of the day here. It says if you have engine that receives 660 joules of heat from a hot reservoir and gives out 420 joules of heat to a cold reservoir, what are the work done and the efficiency of this engine? Okay. So basically, for the heat engine, there's a couple equations you need to use. One is the work done by the engine is equal to Q, the heat it takes in the hot reservoir minus the heat it dumped to the cold reservoir. The second equation will be the efficiency is equal to W over QH, or E equals to 1 minus QC over QH. Okay. And I think you guys can do this with those equations. All right, so we can take a look here. for A, it's asking you work done. So simply it tells you QH basically. So that's 660 joules, and then QC 420. So you just subtract 420 from 660. That gives you 240 joules. Okay, so that's the work done. And then for B, you are looking for efficiency, which will be this guy, right? You can take that guy, 240 joules divided by 660 joules. Okay, that will give you about 0.364. Or you can also express this in percentage wise, so 36.4%. Okay, you can also do it this way: E equals to 1 minus 420 joules divided by 660 joules will be the same. Okay. All right. So I think most of you guys got this one right. All right, but just in case if you have questions, you can let me know. All right. So if you are clear, we can then check on the next section here. Talks about and what's the maximum efficiency an ideal engine could have. Okay, so for an ideal engine, it's also called Carnot's engine. So if you see a word Carnot's engine, that means we are assuming this is an ideal engine. But just keep in mind, in reality, we couldn't have an ideal engine because for an ideal engine, then the process will be happen so slowly. So that's the assumption there. So the process can happen so slowly because so it's a reversible process. In reality, you rarely would have a ideal process. Okay, so for each process to happen, there's a something has been done to the environment that cannot be recovered. Okay, so just keep in mind in reality that's what happens. But we can see what's an ideal one, so then we know what's the upper limit of an engine can do. Okay, in reality, you can probably like design the machine so carefully that it can approximate, you can like approaching the higher limit of efficiency, that, but you couldn't never reach it. Okay, all right. So this is for an ideal engine. Okay, so you would have hot reservoir here if you know the temperature TH, okay? And then you would have a cold reservoir if you know its temperature TC, all right? Then the heat will flow from the hot object through the engine to the cold object, and then during the process, part of the heat takes in will be converted into work. Okay, so this is what happens. Now, according to the efficiency, is equal to work divided by QH, right? And then we are just taking the absolute value over here. Okay, so then QH minus Q or minus QC divided by QH. Basically, that's it, what the definition says. Okay, so for an ideal process to happen so slowly, so then this is what you would have. You will have a ideal isothermal process to start with. Okay, and then you will have adiabatic expansion. All right, so that means if this is well insulated, or if you can have this happen so quickly, and then when it returns, it goes through C, from C to D. This is also an isothermal process, and then adiabatic compression goes back there. Okay, so you can calculate by using the ideal gas law here, right, and then calculate what's the ratio between what's the work done from here to there, all right? And then that should be related to for isothermal process. If you guys remember last time when we said work done should be equal to a natural logarithm function, all right? So nRT, natural logarithm function of the final initial divided by the v sub c divided by v sub d. It should be the final divided by initial, but we are looking at the work done underneath this curve, and then also work done underneath that curve. Okay, so you'll take the difference, all right? But I'm not going to go through the detailed algebra here, but this is the result you'll be getting. Okay, so for QC over QH, okay, so QC then is going to be related to this equation, and then QH is going to be related to an equation here. All right, so the two ratio of the two Qs, it's going to be equal to the temperatures of the two. Okay, so it takes heat from the high temperature reservoir and then dump heat into the low temperature reservoir. Okay, so basically you can tell from there. So the heat is proportional to the temperature of the reservoir. Okay, so that's your conclusion there from the algebra if you do QC over QH from these two expressions. Okay, and then also combining with ideal gas law, you will find that VC over VD is equal to VB over VA. So then the efficiency for a Carnot engine, the ideal engine, or the maximum efficiency possible, that's equal to 1 minus QC divided by QH, which is also just determined by the temperatures of the two reservoirs, TC and the TH. Okay, so E then also equals to 1 minus TC over TH. Okay. Now the fact that we have absolute values here is because for this natural logarithm function, it might be negative. Okay, but we just care about the absolute value of it. Okay, so just in case you are wondering. All right. So if you have an engine that is a Carnot engine, then efficiency can be determined by the temperature of the two reservoirs. Okay, so that's the conclusion here. Now let's take a look on the example on the Carnot engine here, the efficiency of that. So this one says a Carnot engine takes in 2000 joules of heat from a reservoir at 227 degrees Celsius, and it does some work and discards the some of the heat remaining to a reservoir at 77 degrees Celsius. So what's the efficiency of this ideal engine? Now you want to do for A here efficiency, because it says this is a Carnot engine, so you can use this. All right, efficiency equal to 1 minus TC divided by TH, because the two T's are given. All right, and then in B, it asks you what's the work done. In C, it's asking you how much heat is being dumped to the surrounding. Yes. So which means QC. All right. For any engine, this equation still applies. Okay, so you can take that down. So you're probably going to just use this equation. In addition to that, you are going to use this as the other equation. Okay, so I think two equations should be enough here. Oh, actually, a third one you would need. E equals to W over QH. Okay. So you'll need three equations on this one. All right, so let's see. There's a couple of responses in there. We can take a look here. So efficiency, because it says this is a Carnot engine, so you can use this, right? E equals to 1 minus TC, all right? So it says TC is 77 degrees Celsius, all right? And then divided by TH227, all right? So you want to be careful about the units given. So the two temperatures are given in Celsius, all right? You should consider converting into Kelvins. So that means you add 273 to each of them, or 273.15, okay? So that gets your temperature in Kelvin, okay? Because this time you are doing TC over TH, all right? You are not doing TH minus TC, so you have to convert them into Kelvin, okay, the SI units, okay? So otherwise, I think this is something you want to pay attention. Otherwise, you guys should be good after that point, okay? So this will give you 0.300, okay, or 30%, okay, of efficiency, all right? For B, your work is equal to, if you look at this guy, so these are two other equations. You can do either this one, QH minus QC, but you do not know QC, right? It's not given, it only gives you QH. So then you will just have to use the E you got from part A. So E equals to W over QH. So then W equals to, you multiply both sides by QH, right, to get your W. So E multiplied by QH, okay? So 0.3 multiplied by QH are 2000 joules. That would be 600 joules on that. After you have calculated your W, then you can calculate your QC from this equation, okay? So then in that case, QC will be equal to QH minus W, because you can move this guy to the outside equation becomes positive, this to the right becomes negative, right? So let's get to that, let's get to that, okay? So 2000 joules minus 600 joules, that gives you 1400 joules of heat being dumped, all right? All right. So I think this is the numbers here are pretty much they are very close to a real engine of your car. Okay, so after the fuel is being ignited after combustion, it reaches probably like 200 degrees something in Celsius, and then when the exhaust heat being dumped to the environment, it's roughly about maybe 70 or 80 degrees. Okay, so that gives you a sense that if your car's efficiency is about 30%, then it's actually very good. All right. But that also tells you that you have about like 70% of energy being wasted during the process. Okay. So the car engine, it's actually not a very high efficiency engine. Okay. So it gives you, you have rough idea of how much energy is being wasted during the process. All right. Okay. So if you are clear, we can check on next. Um, so other applications of thermodynamics. So for example, the in winter right now, we use heat pumps, or we need heat a lot. Sometimes we need heat pumps, okay? So this is how heat pumps or refrigerator will work, okay? Because for heat pump, it actually takes heat from a cold reservoir and then put it into a hot reservoir. So imagine if you have a heat pump in winter, it takes heat from outside air, but it dumps the heat into the room temperature, right? Outside air is colder, the room temperature is hotter. So in that sense, the heat is flowing from lower temperature object to higher temperature object, right? But it cannot happen spontaneously. You will have to use the heat pump here as the additional energy here to make it happen in that way. All right. So heat pump and refrigerator, it's kind of reverse process of the heat engine. Okay. Because for a heat engine, it takes in heat from a cold reservoir and then dump the excess heat to the or it takes heat into from the hot reservoir and then dumps heat into the cold reservoir. During the process, it does work. Now, for either heat pump or refrigerator, it does the other way around. It takes heat from the cold reservoir and then dumps heat to the surrounding the hot reservoir. Okay, so basically, this is the schematic drawing for a refrigerator. Okay, so the inside, the food you have inside the refrigerator, it's cold, right? It's usually cold. So you take out heat from the food, and then during the process, the compressor of the refrigerator does work, all right? And then dump the excess heat to the hot reservoir of the room temperature of the kitchen, okay? So this is a reverse process of the heat engine, okay, which takes heat from hot reservoir, does work to the surrounding, and then dump heat to the surrounding. All right. So nevertheless, here in this case, you can see that heat that has been taken from the cold reservoir, in addition to the work done by the engine or the compressor in this case, that goes to the hot reservoir. So QC plus W equal to QH, all right? The same as here, when you have a hot engine, it takes in QH and then QH will be divided into two parts, W and QC. So this equation still is valid, or W equals to QH minus QC, all right, either way. Now the work is coming from from the energy coming from electricity. Okay, so it takes in energy from electricity there and then add it to this to make this happen. All right. Now, for refrigerator or heat pump, okay, you want to know how much energy is needed for it to be working. So then, in that case, you are properly you'll be focusing on like how much heat it can takes away from the cold reservoir or the food under how much electricity you are using or the amount of electrical energy you are using. Okay, so this is called the coefficient of performance for refrigerator, or COP as abbreviations. COP is equal to QC divided by W. All right. So in that sense, if you have a refrigerator that has higher COP, that means it's more efficient, right? Because for the same amount of electricity needed, you will take out more heat from the food, okay? So when you are buying a refrigerator, look for a COP, the higher the better, okay? All right, we will take a look on the example of a refrigerator here. It says it has a COP of 1.75. It absorbs 3.45 times 10 to the fourth joule of heat from the low temperature reservoir during each cycle. How much mechanical work is required to operate the refrigerator for a cycle? So you're looking for, in A, you're looking for W. So W, that's what you're looking for. In B, you're looking for how much heat does the refrigerator discard to the higher temperature reservoir. So that's the QH. You're looking for QH. All right. This equation still is valid over here. QH W equal to QH minus QC, or QH equal to QC plus W. It tells you COP, which is defined as QC over W. Okay. And it tells you QC, so you should be able to figure out what's W and what's QH there. All right. So we will take a look here together. So it tells us the coefficient of performance. So that's COP. Okay, so COP is 1.75. And then you can use this equation to calculate what's your work. Okay, how much mechanical work is required to operate this in a cycle. So um, so you're looking for W. So basically, you move W to the other side equation, you move this guy to this side over here. So then W equals to QC over COP. Okay, so that's what you should set up. 3.45 times 10 to the fourth joules divided by 1.75. Okay, that gives you about 1.97 times 10 to the fourth. All right, that's how much work is needed for each cycle. Now, for QH, then it would be QC plus W. Okay, so 3.45 times 10 to the fourth plus 1.97 times 10 to the fourth, okay, which would be 5.42 times 10 to the fourth joules. Okay, all right. Questions you guys might have on this one? All right. So if you guys don't have question on that one, we can move on here. So for air condition, so it's pretty much the same as the refrigerator, right? You just imagine the whole house is an air conditioner, as a refrigerator. So inside the house is the same as inside the refrigerator in that sense. Okay, so AC is the same mechanism as a refrigerator. Okay, so it takes heat out from the inside of the room, the house, and then with the work, mechanical work done from the AC, and then dump the excess heat to the outside surrounding. Okay, so in this sense, the cold reservoir is the inside of the house. The hot reservoir is the outdoors. Okay. All right. Now in that sense, you can see like AC is always they are, if you have an AC within the house, then it will not work. Okay, the whole house will, the temperature will get up because amount of heat can be removed is less than the amount of heat that is added to the room in that case. Okay, because QH is always greater than QC. All right. The same reason is if you don't have AC at home, you are thinking about just open the door of refrigerator to cool up the room, that will not work because the QC removed should be less than the QH that is added to the room. Okay, so in that sense. All right. The heat pump. So the heat pump is the same as an AC, but it's in the reverse process. Okay. So what happens here in the winter when you turn the heat on, what it does if you have a heat pump. Okay. So that's the scenario. If you have a heat pump, then it takes in heat from the outside cold air with the work being added to the heat pump by the electricity here, then the total heat QH is being added to the room. Okay, so that's how the room can warm up, but you actually take less heat from the cold environment, the outside. Okay, so that's how a heat pump works. All right. Um, if you have an ideal heat pump, let's assuming the engine you have or the compressor you have for the heat pump is ideal. So then the Carnot efficiency or Carnot coefficient of performance will apply here. Okay, so for a heat pump, what you are interested in would be like the amount of heat can be added to a room under a certain amount of the work is required. So coefficient of performance for a heat pump is QH over W, where for a refrigerator is QC over W. Okay, so for a heat pump it's QH over W. All right, and then if this is an ideal heat pump, then QC and QH are related to TC and TH respectively. So then W can be calculated with this expression over here. Okay, so W can be equal to QH times 1 minus TC over TH in that sense. All right. I think we are going to stop here for today, and then we will be talking about entropies next time. Okay.
Thank you.